shall look at application of ordinary differential equation. In the application of ordinary differential equation, it could be related to mechanical engineering, electrical engineering, chemical engineering, petroleum engineering, in fact all aspects of engineering, even biological engineering. We shall now look at a typical relationship in electrical circuit model where we look at voltage across the inductor plus voltage across the resistor is equal to voltage of the circuit, total voltage running the circuit. And this was the work of Sir Kirchhoff's. This is Kirchhoff's law in electrical engineering. Voltage across the inductor is L di dt, and voltage across the resistor is current multiplied by resistance according to Ohm's law is equal to total voltage, let us say the electromotive force. So we have been able to build a first order linear differential equation if we divide through by L. That gives us the I dt plus resistance over the inductance multiplied by current is equal to electromotive force all over inductance. Now, this aesthetic equation is very fundamental in electrical engineering. Take note that linear first order differential equation is characterized by dy dt or dy dx plus qy equal to q if we are using x function. So, and the solution to this expression is y exponential integral p dx equal to integral q exponential integral p dx differential x plus arbitrary c. Now, this is purely a concept of ordinary differential equation that has to do with linear differential equation. So, but this is an applied linear first order differential equation. And if we assume here that P is equal to resistance over inductance as it relates to this linear first order differential equation, now, and we also assume that Q is equal to the electromotive force divided by the inductance. So if this is to be imputed into this relationship, the solution formula for linear first order differential equation that is characterized by y exponential integral p dx is equal to integral q exponential integral p dx differential x plus c. Note that this q does not mean charge, it's just a letter, it's not charge, electrical charge. Neither is a capacitance of a capacitor, no, it is constant c. It is constant c. So to further this relationship, y here is going to be current because this is dy dx, this is di dt. So y is going to be current exponential integral p. P is r over l as depicted there, to be r over l multiplied by differential t, because the I dt, the y dx. So dx is dt, and this is a transformation into the linear first order differential equation format and the solution format. So this is the replica of the translation, and this gives us integral of q. Q is going to give us electromotive force over inductance. Now, exponential integral p. P is r over l dt plus arbitrary c. Note that the integrating factor of this electrical application, the integrating factor here, is equal to exponent integral of r over l dt. That is the integrating factor. That is the factor that multiplies the left hand side and the right hand side. So we can further this operation. We can further this operation in a like manner as a continuity of the relationship to give us, it will now be current exponential integral r over l dt gives us r over l t is equal to integral q, and q was given as E divided by L, the inductance. Now, if it is this relationship, it means, since it's a constant, to bring it out, 1 over L, integral of exponential R over L, t plus arbitrary dt plus arbitrary c. Now, take note that to avoid excess ambiguity, we could choose to use K here, constant K, rather than C, so that it does not connote capacitance of a capacitor, since it's application, applied problem. So this is applied problem. This is what we are going to work with. K, not C. Take note, it is not that C is wrong, but because C connotes capacitance of the capacitor in electrical circuit models, we could consider it from that perspective. We are talking of a circuit that has to do with a resistor. This is a typical sample of this type of circuit, and it has to do with the inductor. This is the nature of the circuit. Now, the electromotive force running the circuit is here, so that we have a feedback system. This is the inductor, this is the resistor. So, for this flow of current relationship, and current is flowing with respect to time. So this is a typical circuit model for this relationship. So to resolve it finally, we have current exponential resistance over inductor multiplied by time is E over L. When we integrate R over L, we have L over R exponential R over L t plus K. Assuming that the model you were giving initial value. When we talk of initial value, that's point of origin, current I0 is equal to 0. That is to say, current itself is given as 0 and time is equal to 0. So if time is 0 and current is 0, that is to say that we are considering an IVP problem, an initial value problem. Initial value problem. Initial value problem is after solving the differential equation, you'll be given values, numbers to fit in for some of the variables to get the value of constant K. So, however, at this point, inductor cancel inductor, we have current function of time exponential R over LT is equal to E, electromotive force, divided by R, which is the voltage, the total voltage running the circuit, exponential R over LT plus arbitrary constant K. Yes. So now, if we are saying current at when current time is 0, current is 0. So that is to say, this will be 0 multiplied by exponential R over L 0 is equal to E over R exponential R over L 0 plus K. So that at the end of the day, this is 0, this is 0, but this is 1, exponential 0. This will give us 1. So we'll be having 0 is equal to E over R plus arbitrary constant K. Since exponential 0 gives us 1, because this multiplied this gives you 0, so it means that K is equal to minus E over R. If K is minus E over R, we are going to place this in equation 1. We now put it in 1, put in 1 to get the final result of the relationship. And this will now finally give us current function of time is equal to exponential R over L t is equal to E over R exponential R over L t. Now, because of this relationship, note that current is multiplying this, so it is a dot product of the entire function. The equal to is here. I'm borrowing relief from this equation. Note, this is what we are imputing. We are relating it back here, just to get to fit in the value of K, since K is minus E over R. Now, minus E over R. So you can further the operation by perhaps collecting E over R as a factor. When it is collected as a factor, so it gives you current multiplied by exponential R over LT equals to E over R into exponential R over LT minus 1, all in bracket. Furthermore, you can leave it this way. You could also remove the multiplication sign and make it a closed multiple on onset as I is a function of time to mean. You can help the expression here or factorize here out as your final state. This is the electrical resolution value for an inductive resistive circuit or a resistive inductive circuit, an RL circuit. This is an RL circuit model. RL circuit. It belongs to first order circuit in electrical engineering.